All right, let's get into it. We're about to tackle one of the biggest, most mind-bending questions in all of science. What is the ultimate fate of, well, everything?
For the past 25 years or so, the story of our universe seemed pretty much settled. It kicked off with the Big Bang, and it's been expanding ever since. But here's the key part. We thought it was accelerating, pushing galaxies further and further apart at a speed that just kept increasing.
And that led to a pretty grim forecast for the far, far future, a scenario we call the Big Freeze. The idea was that the universe would just expand forever, getting colder, darker, and more empty until all the stars flicker out. A very cold, very quiet end.
But what if that core idea, the one that won Nobel Prizes and basically defined modern cosmology, is flawed? What if the universe isn't actually running away forever? Because some new evidence is popping up that suggests we might have to completely rethink the end of the universe as we know it.
So, to really get why this is such a big deal, we have to rewind a bit. Let's look at the original evidence. How did we get so certain that the universe was speeding up in the first place?
Well, the story really gets going in the 20th century. First, you had Einstein, who actually put a little fudge factor in his equations to keep the universe static. He later called it his biggest blunder, especially after 1929 when Edwin Hubble showed that, nope, the universe is definitely expanding. For decades after that, everyone just assumed gravity had to be slowing it down. But then, 1998 happened, and a discovery was made that just changed the entire game.
And the key to that discovery was this very specific, very special kind of cosmic explosion, a Type 1a supernova. Now think of these things as standard candles. It's a brilliant analogy, because these particular stars always explode with the same predictable brightness. They're like cosmic lighthouses. If you know how bright the bulb is supposed to be, you can figure out how far away the lighthouse is just by seeing how dim it looks.
And here comes the bombshell. In 1998, astronomers were looking at these distant supernovae, our cosmic lighthouses, and they found that they were fainter, dimmer than any of our models said they should be. And really, there was only one way to explain it. They had to be even farther away than we thought. The only way for that to happen is if the very fabric of space between us and them had stretched more than expected, pushed apart by some kind of mysterious anti-gravitational force.
This conclusion was absolutely revolutionary. The universe wasn't slowing down under gravity's pull. It was speeding up. And this wasn't some fringe theory. It was so foundational that the scientists who led the teams got the Nobel Prize for it in 2011. The accelerating universe was now a scientific fact.
Now, to explain why it was accelerating, scientists came up with a new recipe for the cosmos. And what they proposed was an idea called dark energy. And get this, it's not some minor ingredient. It makes up something like 68% of everything in the universe. Another 27% is dark matter. So the stuff we're actually made of, all the stars, the planets, you, me, is less than 5%. Our whole view of the universe became dominated by things we can't even see.
Okay, so that's the established story. But now, our cosmic detective story is about to take a really sharp, really unexpected turn. Because that central piece of evidence, our trusty cosmic lighthouses, is suddenly under some very intense scrutiny. You see, for the whole accelerating universe theory to hold up, our standard candles have to be truly standard. Their brightness needs to be reliable, consistent, no matter where or when they explode in the universe's history. But what if they're not?
Some really fascinating new research is suggesting there might be a flaw in our assumption. It seems that the actual brightness of one of these supernovae might be connected to the age of the galaxy it's in. The most distant galaxies we see are also the youngest. We're seeing them as they were billions of years ago. And they might have produced intrinsically brighter supernovae. So if that's true, when we see a distant supernova that looks dim, it might not be because it's super far away due to acceleration. It might just be that it was a different, less bright kind of explosion to begin with. And that changes everything. It opens the door to the idea that dark energy isn't some constant, but a force that could actually be fading away.
And if dark energy really is weakening, then the entire future of the universe looks completely different. That cold, lonely big freeze isn't the only ending on the table anymore. A much more dramatic fate suddenly becomes possible.
This lays it out perfectly. The old story, on the left, is that dark energy is a constant force that wins the cosmic tug-of-war against gravity forever. The universe just keeps expanding. But in this new scenario, on the right, if dark energy is a fading force, then gravity, that patient, persistent force of attraction, is going to win in the long run. The expansion would slow down, grind to a halt, and then reverse. The universe would start to contract, pulling everything back together for a big collapse, heading right back to that hot, dense state where it all began.
So where does all this leave us? It might feel like we're back at square one, but that's not it at all. This doesn't represent a failure. What it really means is that we've stumbled upon a deeper, more profound mystery. And honestly, this is what science is all about.
So the main takeaway here isn't that we have the final answer. It's that the question has just gotten so much more interesting. Is dark energy a fixed property of space itself, like Einstein once thought? Or is it some dynamic field that changes over cosmic time? The entire fate of our reality hangs in the balance. And trust me, the hunt for that answer is on. There's a whole new generation of incredible instruments being deployed to map the cosmos with a precision we've never had before. Projects like the Euclid Telescope and DZ are building these massive 3D maps of the universe, specifically designed to track the history of its expansion and, hopefully, solve the dark energy mystery once and for all.
Which brings us to one of the most fundamental questions we could possibly ask. Is this mysterious energy the force that's going to tear everything apart into a cold, dark nothingness? Or is its fading power a sign that gravity will eventually pull us all back together for a fiery cosmic reunion? The search for that answer is truly one of the greatest adventures in human history.